Hey, good morning, guys. I am here to talk to you guys about how to calculate volume using integration, kind of like what we talked about last time, except we're going to be rotating about a given axis. And so, actually, what's going to happen, like 5 minutes, is that all of those cross sections, like what we were doing last time, are all going to be circular discs. And so I wanted to start with some pictures to just kind of show you guys, because we have all these different cases of what can happen. So the first, let's take a look at this picture right here. So I have this function. Here's my f of x. It could do lots of things. And so I'm interested in taking this function and creating cross sections, circular cross sections, like what you see in this picture right here. And then I'm going to integrate them from A to B and create volume, and have it be rotated about this axis. A lot of times I'll kind of draw a symbol like that. You see one right there. Helps me to see. So the three cases we're going to look at today is where you have no hole. A lot of times you'll see, like if you see in this picture down here, there's a hole cut out of the middle. Well, this is one where there's no hole cut out of the middle, kind of the most basic type of problem, and you're revolving around the y-axis. Sorry, x-axis. The other kind, or another type, is where you do have a hole, so you have to think about how to kind of cut this volume out of what you're calculating. And this is revolving around the x-axis. All right, another type that we're going to look at is where you could have a hole or you could not have a hole, actually. I gave you a picture with no hole, but now you're revolving around a different axis. So this would be the line y equal 12. We could also do all of these things with respect to y, and so then everything would just be kind of flipped vertically. Um, but let's look at some of these special cases. One thing I have done for you, if you guys want to write this stuff down, is I have kind of, uh-oh, can you see it all? Yeah, you can see it all. So I've kind of given you guys some steps. And here's the idea is that it's a circle whose radius is modeled by some given function. So just like before, we take all whatever cross section we wanted and we would use the functions that were given to model what we needed to calculate the area of that cross section. You know, if it were a rectangle, then we would need the base times the height. If it were an equilateral triangle, we would just need the base. And then we would take whatever function we created to model that side and plug it into the formula for that area. But now, since we're just using circular disks, so we're only using the formula for a circle, which is pi r squared, all we have to do is use our function to model the radius. And then we take this radius and we plug it into the formula for a circle, pi r squared. So here are kind of the questions that you want to check. You want to check first if you're revolving around some line where c is not 0, or are you just revolving around the x or y axis? Because you kind of have a different formula. And I don't really think it would be important to remember these formulas. What's actually kind of happening here is that you're looking at the area between two curves. One curve being the line that you're rotating around, C, and then the other being your function. Another question you could ask yourself is there a hole? And if there's a hole, then you take and you calculate the area, sorry, the volume of your hole, and then you subtract that from the volume of everything on the outside. So let's try some examples. Oh, that's really tiny. Let's make that bigger. Just a little bigger. There we go. So I really liked these examples just out of the textbook because they gave me some really great pictures. And I thought it would be a lot easier for me to show you guys what was happening if we had good pictures. So they want me to calculate the volume of the solid. We're going to rotate the region under y equal x squared. So here's my graph y equal x squared. So if you were going to graph this on your calculator, this down here would be the graph you'd see. And then we want to go from 0 to 2. So I would think, okay, what kind of function am I going to have to get to model the radius of this cylinder, this circle that I'm going to create? So I think that since my radius is just going to be the distance between my curve and the x-axis, then my function that models my radius is just going to be x squared. So this is going to be equal to r. And then I ask myself, is there a hole? And there's no hole. Am I integrating with respect to x or with respect to y? And they tell me I'm rotating about the x-axis, which means I'm integrating with respect to x. And then they give me my bounds. So my bounds are going to be 0 to 2. So now that I have my radius, I'm going to write the formula for the area of that circle. So that's just going to be pi times r squared. So this is going to be pi, r is x squared, all squared. So now I integrate my area from my lower bound to my upper bound. So this is going to be the integral from 0 to 2 of pi. So I'm going to put that constant out on the front, x to the fourth dx. And then I'll integrate this. I know you guys like to use Math 9, but I'm just going to do most of these by hand today. I think there's one. So it'll be pi over 5, x to the fifth, which will give me the exact value of 32 pi over 5, or if you approximated it, it's approximately 20.106. So it's really not bad. My biggest problem is just integrating r and not integrating the area. So forgetting the pi and forgetting the extra squared there and just integrating f of x, which is all that's going to do is just give you the area under the curve. It's not going to give you any volume. So now let's try one that puts a hole in the middle. So we're rotating about the x-axis because they tell us that we're about the x-axis. They tell us that we're going to go between these two curves, x squared plus 4. So I would, put that in my calculator, make a graph, look at that, and then y equal 2. And so there's that line right there. So right here you can see what happens, as I rotate around, that I have this hole cut out of the middle. Now, I think it's better sometimes, especially when you know your hole is a perfect cylinder, to just write the hole instead of trying to create some function, but just say, okay, my hole is a cylinder of radius 3. Then, my area for that is just pi times 3 squared. That's going to be that circle. And, when I integrate it from my bounds, I'm going to get the volume. And not try to get an f of x or anything. That is especially helpful when you're rotating about a line that's not the y-axis or the x-axis. But anyway, so I see I have this little hole first, so I'm going to deal with the hole first. Let me write a few things down. I have a hole. I'm doing this with respect to x. These are all the things I have to think about. And then, so that means I need an inner radius. So my cylinder, since this is the line y equal 2, just has a radius of 2. So my r inner is just 2. My r outer, that's going to be all of this area right there, all the way down to the x-axis, because I'm cutting the hole out of it. So it's just going to be modeled by the function. I don't have to do anything funky with it. So my r outer is just going to be x squared plus 4. So now that I have both of my radiuses, I'm going to write the formula for both of my areas. And then I'm going to integrate them. Always the areas, the area using r outer minus the area using r inner. So my area here is just going to be pi times my radius, which is x squared plus 4, all squared. My area for my inner is just going to be pi times my radius, which is pi times 2 squared. Now I integrate within my bounds. They tell me my bounds are 1 to 3. So I integrate from 1 to 3. And it's going to be area for the first minus area for the second. I'm going to go ahead and take the pi out of both of them. It just makes it easier. So this is x squared plus 4 all squared minus 4 dx. Now you could, well, you probably, if you wanted to do this by hand, take this piece and multiply it all the way out. You couldn't use u sub because you don't have an extra x there. So I've kind of done it all in one step. If you don't believe me, then you can, I don't know, FOIL it out yourself and see what you get. So I'm still have this pi on the outside. So after I FOIL it out and I integrate it, I get 1/5 x to the 5th minus 4x squared plus 12x. And I'm taking this from 1 to 3. And so when I do all this math, I get 202 pi over 5. So let's recap just a minute, because it seemed almost too easy, right? It wasn't really a whole lot of work. So I took and I looked first for my inner, right? And I found out my inner hole was just going to be a cylinder of radius 2. So I start by writing the radius down for each piece. The radius for the outer, the radius for the inner. And then once I have that, then I write my area equations. Because the last thing I want to forget is to just integrate the radius and not integrate the area. So once I create my area equations, then I integrate from my bounds the area of the first minus the area of the second, and then that's what I get. All right, so let's try another, a little more complicated. Let's try hole and no hole, rotating about, one is going to be about the line y equal 12, that's going to be the no hole, y equal 15 is going to have the hole. So first we're going to do the no hole. So here's the function. My function is 9 minus x squared, so you can see it right there. And then my line I'm going to rotate about is 12. So I think that this is going to be the radius of my circle, the distance between those two. And then I'm just going to be rotating about this line. So I don't even think you really need to think about that fancy formula that I gave you on the second page, I think it was. I think you guys just need to think, okay, I want the area between these two curves. So there's my area right there. So this is my upper curve is 12, my lower curve is 9 minus x squared. And then since I don't have a hole, I can just write my radius as r is equal to 12 minus parentheses 9 minus x squared. So now I'll just clean this up a little bit because I like that better. So it's going to be 3 plus x squared if I simplify. So now I want to take and I want to write the formula for area. So pi times my radius, which is 3 plus x squared, all squared. So now I'm going to integrate area. So I'm going to take this up here because I didn't give myself a lot of room. I'm going, as you can see, from 0 to 3. I think they told me that in the problem. Yep. Right. And so I go from 0 to 3. I integrate area. So this is pi times my area, which is 3 plus x squared, all squared. And then once again, if I want to do this by hand and calculate the antiderivative, I've got to FOIL that thing out. So if you guys want to FOIL it out, you can calculate the antiderivative also. And this is what you're going to get. So you're going to get, well, I'll FOIL and do the antiderivative at the same time. So we're going to get a pi on the outside. We have 9x plus 2x cubed plus 1/5 x to the 5th. And I'm going from 0 to 3. So if I plug it all in, I do all the math, then I end up with 468 pi over 5. So that's going to be my answer. So really not much different. You just have to realize that you're finding the area between those two curves, and then you're just taking, and that's your radius, and then you're going to make your circle. Integrate that. So let's check out this hole. Now we're rotating about the line uh, y equal 15, which gives me this hole right here in the middle, since I'm still looking between the curves y equal 12 and y equal 9 minus x squared. So my hole is just a cylinder of radius 3. So instead of trying to create some big fancy function for that, I'm just going to say my r inner is equal to 3. And now let's think about the r outer. I'm pretty sure this is going to be the same r outer that I had in my previous problem. Oh, wait, except no, I need the whole r. So I don't just need these pieces that I did in green. I'm going to scratch that out. I need to go all the way from 15 all the way down to the curve. That way I get, that will be all the area without the hole. And then I cut the hole out of it by subtracting, pi times 3 squared. The integral of that, actually. So then I take and I write my r outer, and that's going to be the top here, the 15, minus my curve, which is 9. Oh, ran out of room. 9. No, gosh. Sorry, failing. R outer is my top function, which is 15 minus 9 minus x squared. There you go. I got it. So I'll simplify this also, so that means I get 6 plus x squared. So I'm going to write both my areas. So let's do the area for my inner first. So the area for my inner is just going to be, this is 3 pi times 3 squared. And now we need to find the area for my outer. And that's going to be pi times my radius, all squared. So now let's take and let's write out my integrals. So we are going to be integrating from 0 to 3. Yep, same as before. So it's going to be my outer. I'm just going to go ahead and put this pi on the outside. So this is going to be 6 plus x squared, all squared, minus my inner, which is just 9. So then this, and dx, of course. So I'm going to have to FOIL this and then, subtract the 9 and do all that to get my antiderivative. And so when I come up with my antiderivative, it's going to be pi times 27x plus 12, no, sorry, plus 6x squared plus 1/5 x to the 5th from 0 to 3. And I just realized that I made a mistake on mine. So I think I need to make a correction. So I'm going to pause it and I'll be back in just 1 second. Alright, I found my mistake. I apologize. Better than me fumbling around. So it seems that I don't know how to FOIL, because this now should have been after I FOILed 12x squared, which after I integrated would give me 4x cubed. There we go. And then I'll get my answer. And it ends up being 1188 pi over 5. So let's recap just for a second. So we took and we found the area between these two curves, used that as our radius. So here is our formula for the radius. Then we created a function that modeled the area, and then we plugged that in and we integrated it within our bounds. Next, for the other problem where we had the hole, we determined the radius of our hole, which was just 3. We determined the radius of our outer, which was the distance between the axis that we were rotating on and the curve. Then we wrote our area function. Our area for our outer was that. Our area for our inner was that. And then we subtracted the outer minus the inner, and we integrated from the bounds. All right, we got one left. Let's talk about with respect to y. So let's zoom in just a little bit. So they give us, fun, a function in terms of x, and they want us to integrate it with respect to y. They tell us, because we are going to integrate about a vertical axis. So anytime it's a vertical axis, you can see the little red marks, then that always means it's going to be with respect to y. So I'm going to start off by just solving my function. I know that I'll need it later for x. So this gives me x is equal to the square root of 9 minus y. So now let's take a look and see what else we have. So I see that we have a hole. We're integrating with respect to y. So I'm going to need to find an outer and an inner. So if I look at this hole, my function ends, I could see this is the piece of my function. And, you know, when I accumulate area, it's going to accumulate it from the y-axis to my function. So here's my cylinder. It sits on the line x equal negative 2. So the distance between that and the y-axis is 2. So my inner is just going to be a cylinder of radius 2. So I'll go ahead and write r inner is just going to be a cylinder of radius 2. So let's talk about r outer. So I have to think of the fact that I'm cutting this hole out. So I don't just want my radius to be from the y-axis, which is right there, to the curve. I want my radius, my outer radius, to go all the way down to the center of this hole. That way I can get all this volume, and then I take and I can cut out my cylinder. So I'm going to go, I can think of it just as the area between two curves. So I'm going to go from there, that's my curve, all the way down to the line x equal negative 2. So I already know that this outer curve is represented by the square root of 9 minus y. So I'm going to take that, and I'm going to subtract from it negative 2, because, you know, I'm just looking for the area between those two curves. Here's my curve, the square root of 9 minus y. There's my curve negative 2. So I've now written my two radiuses, and now I want to do my areas. So my first area, my outer, is going to be pi times my radius, which is the square root of 9 minus y plus 2 all squared. And then my area for my inner, and these should be in terms of y. There we go. And this is just a cylinder of radius 2, so it's just pi times 2 squared. Right, so now we want to take and we want to integrate these things within my bounds. So here's the tricky part. So you could see that this goes from 0 to 3, and my x's go from negative 2 to 3, but this is not what I want. I want the y area. So I see where on my function do I start and stop accumulating area for y. So I start accumulating area for y on the x-axis. It's going to be where y is 0. And then I go all the way up, and I'm actually going to stop accumulating area for y where it's 9. Because if I go all the way here, you know, all the way to where it's negative 2, and I only cut out this cylinder, then I'm going to have a little extra area left up there that I haven't accounted for. But if I stop integrating at 9, and it just kind of, you know, cuts off there, then I can just cut out this cylinder and I'll get the proper volume. So my bounds, I guess I could write this down somewhere. I remember y bounds. My lower y bound is 0 and my upper y bound is 9. So now I can integrate. So I'm going to do the integral from 0 to 9 of my area. So I'm going to pull the pi out. I'm going to do the square root of 9 minus y plus 2 all squared minus 4, because that'd be that piece, dy. So I would take, you could FOIL that thing, you could, and do it by hand, but I'm actually going to cheat a little. I'm going to do math 9. I had to jump over and get my papers. I'd left them. Sorry about that. And so when I integrate this with respect to y from 0 to 9, I end up with 225 pi over 2. So let's recap again, and then we'll be all done. How fun. So we started, I love how I marked all over this thing. See that yellow right there? We started by looking at the inner hole, and we decided that that was just a cylinder of radius 2. Well, I guess first we determined there was a hole, and it was with respect to y. So then we then found our outer, which was the distance from the center of the radius of the hole all the way to the outer function. So that was my function minus the line that ran through the center of the hole, which was -2. Then I wrote both my area equations, and then I integrated those area equations within my bounds. And I got 225 pi over 2. I hope you guys learned something, and I will talk to you guys soon. Thanks.